Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. In this lecture, we simply continue our discussion which was inspired from the last discussion, that is another mode of transport phenomena in turbulent system, that is the viscosity. Okay, that means the transport of the linear momentum. So in the previous discussion, we talked about the diffusion in a turbulent medium, where mostly the density is transported. Now in this lecture we will discuss the transport of linear momentum. And as you know that whenever in a system you have some fastly moving layer which is being adjacent to some slowly moving layer, then both the layers by the virtue of viscosity will try to reduce their relative velocity. So the faster one will try to accelerate the slower one, and the slower one will try to retard the faster one, right? That's the story. Now, what happens if this type of transport phenomena takes place in a turbulent medium? Is there any additional role of turbulence? Okay, so for example, so we just saw that in case of a turbulent medium, in general, if you start from the first principles, just because the turbulent displacements are random, then you can actually show that their mean square displacement, they actually make some linear relation with the time, and for times which are very greater than the correlation time of the system. Okay, so now in this lecture we will try to investigate whether we have same type of effect, that means some effect, whether so what was our conclusion? That the transport of density, or how to say, the diffusion process was actually enhanced by the turbulence process, right? And that was actually very easy intuitively to see that as turbulence means that the random motions of fluid packets from here to there with random velocities, then to be very honest, that this type of motion would surely help in mixing. There is no big surprise, right? Now whether this is the same case for the transfer of or transport of linear momentum, that means if instead of a laminar motion your system has some viscous effect, so is a turbulent medium just show the same type of effective viscous effect, or it can modify the viscous effect to some other value? That's exactly the question we will try to answer here. So for that we have to understand how turbulent viscosity affects the Navier-Stokes equation. Now it is true that we have talked several times about turbulent viscosity, but we don't know how to introduce them. So first of all, we will try to formally introduce turbulent viscosity. So of course we know in Navier-Stokes equation, okay, so if you remember Navier-Stokes equation, so you have terms like del V del T plus V dot nabla V, that is the nonlinear term, and then there should be some gradient of P by rho term, plus there will be some external force term, plus there will be something called this mu by rho divergence of V, plus mu by 3 rho gradient of divergence of V. Okay, these last two terms, they are the you know that they are originated from the off diagonal part of the stress tensor, and they constitute the viscous effects, this one. Okay, now if for simplicity we just take an incompressible fluid, then you know that the resultant viscous effect is totally represented by nu times, nu is nothing but mu by rho, so nu is the kinematic viscosity, nu times nabla square or Laplacian V, this will be the resultant viscous term. okay, or the surviving viscous term. So if this term is there, of course we can easily understand that this is the normal molecular viscosity, and molecular viscosity. And the question is that in the presence of turbulence, okay, whether the viscosity, all the viscous effects are only due to this mu, or there should be some extra effect. So we just write down the incompressible Navier-Stokes equation at first. Okay, one can easily study with compressible equation, but compressible Navier-Stokes equation, but just for simplicity, let us first check that what happens to the linear momentum transfer for an incompressible fluid, because this is first of all analytically simple to handle. Okay, so we just take ddt, del del t rho vi, where of course you know that rho is the constant density. Okay, rho vi is equal to rho times fi. This is the ith component of the body force, this is the ith component of the linear momentum, plus del del xj minus p times Kronecker delta ij. So this is the pressure gradient force minus del del xj rho vi vj. So this is nothing but the inertial nonlinear term. Okay, so if you remember that another way of writing, so one way is of course writing the Navier-Stokes equation as like del v del t plus v dot nabla v times rho and is equal to the right hand side. Another way is to write is del of rho v del t, and then the second term, the nonlinear term, should look like this: rho divergence or rho v tensorial v is equal to minus gradient of p and other terms, right? Exactly, here we are taking this second way of writing, and so this is the nothing but the divergence of rho v tensorial v. Okay, this is the viscous term, and a priori we have not assumed that mu is a constant. We have just made mu inside the del del xj. Actually, also both for rho and mu we have not yet assumed explicitly they are constant, but one thing is true, that here it is evident that the divergence of v part is assumed already to be 0, because otherwise the viscosity would have two terms. Okay, so this is incompressible fluid, and actually rho and this rho, they are practically constant, okay, in both time and space. Now we just recapitulate, or we recall the Reynolds decomposition method, which I introduced at the very outset of this section. Okay, when I was trying to introduce the statistical approach to turbulence. So Reynolds decomposition is nothing but the decomposition of the physical quantities of at every point, okay, every point in space and time, into two parts. One will be its statistical average, plus another will be its fluctuation with respect to that average value. So this is statistical average once again. So the ith component of the velocity can be written like this. So this is mean velocity plus the fluctuation velocity. The pressure is mean pressure plus fluctuating pressure, and this is the body force. Ith component of the body force would be equal to the mean force or the average force plus the fluctuation part of the force. And of course you know that by definition or by construction, any quantity which is fluctuating, for example p fluctuation, its average should be 0, right? That's simple to understand if you take the average on both sides. So this one will be equal to this one, and its average will simply be 0. So that's why we can conclude that all the terms which are linear in the fluctuations, they actually vanish, but for the nonlinear term we cannot say like this. And why we cannot say like this and what exactly we can do, that actually is not very easy to understand. That we can try to see here just by incorporating the Reynolds decomposed expressions in the Navier-Stokes equation, and especially to the non-linear term of the Navier-Stokes equation. So the non-linear term practically comes out to be, because rho is constant, we can simply play with Vi Vj average, and this will be exactly equal to within third bracket. So Vi is nothing but mean Vi plus fluctuating Vi, and Vj will be mean Vj plus fluctuating Vj. Okay. Now when Vi, so everything is inside the angular brackets. So the first term will be, of course, Vi times Vj. Okay, Vi average times Vj average whole average. Now both of these terms are already averaged, so this bigger average would not affect. Okay, so it simply comes out to be Vi average times Vj average, plus the second term will be Vi average times the average will then be over Vj tilde. Okay, that is the multiplication of this to this, and finally you take this average. And as you know, Vj tilde is equal to 0, this term will go away. For the same reason, Vi fluctuation times Vj mean whole averaged gives you also 0. So the fourth term, which is now Vi fluctuation times Vj fluctuations average, this does not go away, and that's exactly which is written over here. Okay, because this is non-linear in the fluctuation, so that's why its average is no longer 0. Of course, you have to understand that if this term is equal to Vi average fluctuation and Vj average fluctuation, then we are done. But this is not true. This one is not equal to average of Vi fluctuation and average of Vj fluctuation, right? Okay, so this term is non-zero in general. And if we write this expression of Vi Vj as we have written over here in the original Navier-Stokes equation, we simply obtain that del T rho Vi averaged is equal to rho Fi averaged plus del Xj minus P average delta Ij, Kronecker delta Ij, minus, now for the nonlinear term we have two terms. One will be rho times Vi average Vj average minus rho times average of Vi fluctuation Vj fluctuation plus mu times del Xj of Vi average. Okay, so this equation is nothing but the evolution of the mean angular momentum. Okay, or mean linear momentum density, not angular momentum. This is the evolution of mean linear momentum density. Okay, now you see, although this is the evolution equation for the mean linear momentum, actually you will see that we have a quantity from the fluctuation, and this quantity is of course non-linear in nature. Okay, this equation for the first time was derived by Reynolds in the year 1895, and this new term which comes here, okay, this simply says that how turbulence affects the mean field evolution of the linear momentum. Okay, and this term is known as Reynolds stress, in similarity with the normal stress tensors. Okay, so this is called the Reynolds stress. Now why this gives us an account for the effect of turbulence? Because this is constituted by the fluctuations, and as we have already discussed in the first lecture on turbulence, that turbulence is mainly manifested by the fluctuations, right? Okay, so now to evaluate, so of course in order to solve this equation we have to have a knowledge of this. Okay, so for mean field evolution we have to have a knowledge of the fluctuations, and that's exactly the point where turbulence is important. Okay, so where we have to think that something will be different from the normal laminar case, because in case of the laminar flow this type of fluctuations are negligibly small or zero. So we are just happy with saying this is equal to this and del del xj of this, this and this. This term is not there because this is very, very small or 0. Okay, but the problem is that how to determine that. One way is to determine that, again we have to study the evolution equation of this one. But if you do the evolution equation of this one and constitute the equation for this, you will see that you will again be trapped in the classic problem of the closure due to hierarchy. That means del del t of 2 point, del del t of, so what is this? This is the fluctuations of 2 point functions, right? So in a sense this is a measure of correlation. Okay, this is the measure of correlation. So the correlation of 2 point, when we are trying to study its evolution, is associated, you can see actually by calculating analytically, it will necessarily associate 3-point correlation functions. And if you want to calculate del del t of this 3-point correlation function, let's say vi, vj, vk, then you will have a 4-point correlation function. So it will go forever. This is the same type of hierarchy problem which we already encountered when we were talking in terms of BBGKY hierarchy. Okay, so what to do? Of course, the solution is that we have to, as we have done also before, that we have to close the system in some artificial way. So one simple way to close the system or to handle this problem is just to say that, okay, this Reynolds trace will be proportional to the velocity gradient tensor. Okay, so if you can do that and you just say that the proportionality constant will be minus some constant, let's just say I call this, for instance, dt, d capital T. Okay, so this is the proportionality constant, then the system is actually closed. And if people try to match this with experiment or observational results, actually surprisingly it is found to match very well. So if you calculate the velocity gradient tensor of the fluctuating parts and you plot this one with this one, the 2-point correlation functions of the fluctuations, you will see that they will give you a linear relation. Okay, and this coefficient will be with a negative slope, of course, and this quantity will be minus d capital T. Now you see, so that is another way to introduce turbulence viscosity or eddy viscosity. So of course one way is nothing but the using the previous discussion of turbulent diffusion. Okay, so what I was trying to say, that here in this lecture I am totally talking about the diffusion for an incompressible fluid. Sorry, I am talking about viscosity for an incompressible fluid. The transported quantity is the linear momentum. Okay, and then we have encountered this constant, and this constant is dt. Now if you remember, this constant, when we wrote the constant or the diffusion coefficient for turbulent diffusion, we also called them that d capital T. Now was it just an accident? Well, surprisingly, it is also seen that the turbulent diffusion coefficient and the turbulent viscosity coefficient, they are also the same. So that's why I wrote here, this is another way to obtain this constant. So what is the message of that? The message is that whether we are talking in terms of turbulent diffusion or in terms of turbulent viscosity, for both type of transport phenomena in turbulent medium, okay, the same constant or the same coefficient, actually the transport coefficient, I should not say constant, the transport coefficient should appear to be the same. And why this is the same? So that is the fundamental question. So dt can be obtained as a diffusion coefficient for turbulent diffusion. Dt can also be obtained as a coefficient of viscosity for turbulent viscosity. Okay. Now it is true that if you remember that when we very briefly discussed the kinetic transport effects or transport phenomena, we showed that there can be three transport coefficients. One is the viscosity, one is the thermal conductivity, and another is the coefficient of diffusion, and they need not be the same. If you, even that you also know from your previous knowledge of kinetic theory, right? Now, for a turbulent case, what happens? This is no longer true. All the transport coefficients, they are the same, and they are exactly equal to d capital T. Okay, and what is this d capital T? So if you, for example, for some turbulent flow, if you can in some way measure the coefficient of diffusion, okay, just studying the diffusion of that medium, then this coefficient will exactly be equal as the coefficient of viscosity due to turbulence. Okay. Now this is because this discrepancy between kinetic transport phenomena and turbulent transport phenomena is simply because in kinetic transport phenomena, the transport process actually modifies the molecular motion. For example, when the molecules are carrying thermal energy, more and more thermal energy, then they are actually getting faster and faster, right? So their motion is modified. Once again, when the molecule is, when the greater number of molecules are, when they are carrying some linear momentum, this is also true that more and more linear momentum means more and more, the molecules are getting faster and faster. Okay, but in case of turbulence viscosity or turbulent diffusion, what happens that the transport phenomena is unable to modify the turbulent motion itself. Although the turbulence causes a modification in the transport phenomena, thereby giving you some effective transport coefficient, which is the normal coefficient plus the turbulence effect, turbulent part. But the transport phenomena cannot give a feedback to the turbulent motion or turbulence motion. Okay, just by motion by modifying the motion of the fluid as a whole. Okay, so the conclusion is that in microscopic kinetic transport phenomena, the microscopic motions or the motion of the transporter is modified due to the transport phenomena, and that's why all the coefficients are different there. Okay, now here with respect to turbulence sees it, every transport phenomena, as a transport of some passive scalar. So let's say for conductivity this is temperature, for diffusion this is density, for viscosity this is some how to say that, some component of the linear momentum, whatever this is, but this is a passive thing which is transported. And when this passive thing is transported in turbulence, that means this transport cannot give a feedback to the flow. Okay, so I think this is a bit advanced topic to discuss. So if you are interested, you can go through the reference books, okay, of this course which was suggested, and of course in any non-equilibrium statistical mechanics book can also be helpful. Okay, so and so the final message is that in case of turbulence, whether this is turbulent diffusion or viscosity, the coefficient of transport phenomena remains the same, and that's exactly what we are trying to say here, that we have obtained this one for the second time actually, one in the turbulent diffusion framework, one in the turbulent viscosity or eddy viscosity framework. Okay, So this is also known as the coefficient of turbulent viscosity or eddy viscosity. Now, coming at the very end, I will emphasize on 2 points. One is that in astrophysics, specifically, this turbulent viscosity is very, very important. Why? Because in general, for explaining the efficient angular momentum transport in normal accretion disk and also in, so I have to somehow write in normal accretion disks and galactic disks. Okay, I mean just the consideration of molecular viscosity is not sufficient, and then you have to take this turbulent viscosity effect to be into account. Another case is that we have already discussed while discussing the effect of rotation, that for slowly rotating stars, after some time, okay, even if at the very beginning, it has some uh, it can develop some differential rotation, but at the end, due to viscous effects, the star actually ends up rotating with solid body rotation, and molecular viscosity is totally inadequate to prevent this differential rotation. Then also you have to take turbulent viscosity into effect. Okay, so these are the points or astrophysical interest for which one should study turbulent viscosity more in detail. Basically, you can see there are research papers on the role of turbulent viscosity or eddy viscosity in accretion disks. Okay, and also in the slowly rotating stars. Please go through them so that you can have you can have an exposure to the current status of the research of the set field. Okay, so this is all about mostly the transport process in a turbulent medium. In the next lecture, I will discuss very briefly the turbulence in an MHD fluid, and also a brief general overview of in a global view of turbulence in the world of astrophysics. Okay, thank you very much.